Hi, this video is the next in a series where I'll be showing my friend how to make a PCB. In this video we'll be looking at schematic capture and also some basic PCB layout. Alright, so let's go to Easy EDA. You don't need to download Eagle, or you could probably use KiCad, or there's a whole lot of other open source things, but these guys will do it all for you, so it's actually quite good.
Does it cost money to use Easy EDA?
No, it's completely free.
Oh,
Alright, so
free.
Let's start a new project.
Yep.
What do you want to call it?
Nerf MOSFET.
I thought we were going to give you a really exciting name.
Oh, I like descriptions.
Alright, okay. So this is the space you've got. You've got components down this side.
Yep.
Design manager. So these are all the sort of common components you've got. So first of all, we need a power supply. So I'll let you drive it. So VCC.
VCC.
Click and drag it in. Yeah. Now if you use a scroll wheel, it'll zoom in out.
Is this like the positive or negative of a battery?
Positive.
Okay.
Yeah.
Alright.
So go back to ground.
This is ground here?
Yeah. And then click on that because you need a...
Do I need a just anywhere?
Oh yeah, put it a little bit further down.
Yeah, space for component.
Yeah.
Okay, alright.
Now if you go to libraries and then search for, maybe type in TO220, you could probably just pick up one of those sort of packages and then go, just see what that one looks like. Yeah, that's 11.
That was complicated.
Yeah. Wonder why that. Maybe put a dash in there. Yes. Okay, so just click on one of those.
Alright, so it's like got 3 holes.
Yeah, it looks good.
Yeah.
Go click on more, because all we'll do is clone. Type in IRLB3034.
Peanut butter fun.
Peanut
butter food. I think jam. Peanut butter and jelly. Yeah.
Okay. Click OK. What you're doing is you're taking someone else's design and copying it.
Oh, so other people have actually drawn this up for a component and added it to the big central library.
That's right.
That's nice of them.
Oh, you've got an IRF 380.
Oh, we didn't actually search for the IRL.
Yeah, let's do IRLB. Oh!
So
there we go.
Someone's already made it, and there you go.
Yeah, perfect.
That look a MOSFET
That's so perfect. All right.
So,
you want to have that. There's going to be a motor in between.
I'll just pop this here for now.
Yeah, just put it there. Put it there. The other thing you probably need is how are you going to connect it up to the motor? Are you going to have screw terminals?
The motors themselves have little solder tabs.
Okay.
Yeah.
All right. So probably.
I just hit escape to get rid of this little component here.
Yeah,
right?
escape. Yeah.
Yep.
So you probably want to go to libraries and look up header. You want a 2-pin header. You want a 1x2. Oh, there we go. Female 1x2.
There you go.
Perfect. All right, chuck it in.
Place.
You've got the motor, and then you've got the power supply as well. So you need 2 of those.
Well,
so
I've got a power supply here.
Yeah, but you've got to be actually define it on the PCB. So this is just a logical representation of the PCB.
Yeah.
You still need to have a physical component
or a spot for it.
Yeah. So you need 2 of those headers.
Oh, okay. So this is for.
Yep. So put that further up there, somewhere in there. So we've got the MOSFET. We need a diode.
Yes, we do.
1N5400. No result. Alright, so
had 5402.
just type in diode maybe. No, that's a surface mount. That's not the one. Oh, that might be looking like it.
Classic diode, I suppose.
Yeah. Now, theoretically, we should be looking at the package type. When you're placing a component, you need to worry about these sort of things, the mounting data, or they could do it vertically if you want to. But I don't think you do.
Oh, no. I don't know about you, but I always feel nervous when things are sticking up.
Yeah. So
that's if you really push a space. That's the only reason why you do that, right?
Yeah. It's a standard axial lead package. So this K dimension, you've got 25 millimeters minimum.
Before the bend.
Yeah. You can actually get away with a lot less, but I think we could probably just use this one. So let's place that one. You want 2 of those. Now, theoretically, we should be naming this properly.
Yep.
So name this 1N5400.
Yeah, it's okay. I may have been calling it IN. I think maybe when I was searching for it, I don't think I was typing in 1N.
Okay, alright, so we've got that sorted out. Do we have everything? Resistor.
I need a picture for a motor, don't I? Oh no. Well, hang on. This is the logical diagram for the whole circuit, or only for the PCB?
For the whole thing.
Okay, so we did the motors as well.
Well, you've got that because you've got one of these.
Oh.
So probably the best way is if we go up here and we say attributes and call it motor. Then attributes.
LiPo, battery.
LiPo, yeah. Clickable.
It's a new kind of technology. It's always improving in battery science.
So this is a logical representation. Right, so you can pick this up, put it over there, and you can attach VCC to that and ground to that, or else you can logically place it in here and connect it up there. Probably the best way is if you actually duplicate this, because then it doesn't get messy. You want to connect those up, and then that's sorted. That's the power supply sorted.
Yeah.
And then you want to connect the motor up to the power supply. Then you want to connect the flyback diode. So you want to have roughly like this. Then you want the arrangement like this, and then you want the resistor rotate left like this, and then ground. And I'm doing most of the work here for you.
Yep.
So that's the rough sort of arrangement. Then you start connecting up the wires. You want to have the flyback diode in reverse to the power supply.
Pointing back.
Yeah.
Yep.
Because the motor will be connected up to here. Like so. Then feeds down into the MOSFET.
Yep.
And remember, this is a pull down resistor. And then connect the source down to there. Let's add this in like this. So we've got that supply. So these are logically connected to this.
Yeah, it's like a, by the way, this is over here. It's like a reference thing. Right, okay. So this D1 is to protect the MOSFET.
Correct.
And D2 is to protect the LiPo, isn't it?
Yes.
Okay.
So let's add a switch. Actually, we need to add another terminal, don't we? That's the one.
Okay.
Place. So we need another one.
Yes, okay. So, yes, I see. I think I want to call it rev switch because, that's the part that everyone calls it in Nerf.
Right.
Because we're revving the flywheel motors. Okay. That's what we're doing. So.
All right, so we've got 3 headers. So this is naturally pulling down to ground. When you unclose this switch, it'll apply a voltage to the gate, which will induce an electric field in there and allow current to flow.
Yeah, it opens up that MOSFET.
Yeah, essentially like a relay. When you release the switch, this turns into a generator and current will flow back up. And because we're not attaching this to a little MCU or Arduino or something like that, we don't need to worry too much. All right, so we've got our schematic.
So this is per motor, right?
Well, you could potentially use it for 2 motors.
I only asked because the reason why it's important is where the PCB is physically going to sit.
Right.
If it's going to be, say, on the handle on the back, then if you're going to do 2 motors, you need to run twice as many leads to the rev switch. The rev motors, the flywheel motors. And those wires tend to be quite thick, high current wires. Right. And there's limited space to run wires past that little channel from the motors back to the main body of the blaster.
Right. These are all standard package types.
Components, yeah.
Yeah, so you could actually potentially replace it with
I mean, if you think about a typical blaster, I mean, a standard blaster is like what you call the strife, and there's not much room up near where the motors are, so your PCB is likely to be in the handle around the back somewhere, which means that you'd be running, you don't want to be running 4 thick, high gauge wires, but there are some other blasters where there's lots of actual room in the front where the motor's located. You can put the PCB there. Yeah.
This is one of the things that you do when you're designing a PCB is you want to put components in that can be replaced by something else. So later on, if you discover a design flaw, or if you discover some other issue, or if a component becomes obsolete, you can replace it with something else. Yeah. So there's always these trade-offs between selecting the component and future-proofing it as well. Yeah. And space and all that sort of thing. So convert to PCB. All right, so this is where you start designing a PCB. Okay. So this is the artistic side of.
It's just about making the most out of your real estate, I suppose. This is like a solving a puzzle, yeah?
Yeah.
Because you've got tracks for your PCB. They have to be able to not cross over each other.
That's right. And you've got high voltage and low voltage. You want to have certain track widths and things like that. You set the board size here.
Oh, okay. Well, I mean, I'm looking at I'm looking at what might typically fit inside the handle of a blaster.
Right.
I'm thinking like this SD card's a pretty good aspiration.
Oh, okay.
To start off with, something like that.
So this is mil. I hate working in mil.
What? As in milliliters?
No, mil.
What's mil?
Thousandths of an inch.
This is how spacecraft get destroyed.
I'm always having to switch between mil and millimeters, and just annoys the heck out of me. What's your board size?
Well, I'm looking at this thing here.
All right, let me get
SD card.
So you want it to be that size exactly? What's that? 35 mil?
I mean, it's small as possible.
Roughly 35 by 25. Let's work off that.
Yeah, okay. I mean, that's a reasonable ask. I don't think people are going to complain too much if they ask to fit something like that in the handle of the blaster.
When you finish your PCB, you create Gerbers, which are just basically information on how the board's going to be constructed. So as part of those Gerbers, you've got drill patterns.
Where they drill the holes?
Where they drill holes,
the 3 holes,
yeah.
Yep.
The routing information, dimensions as well. So if you do an odd dimension, they'll make that odd dimension.
They'll charge you more too.
No, they don't.
Oh, really?
No, any weird size you want, and they'll do it. And they'll just take whatever you give them to.
Yeah.
So, all right. So this is the fun bit. You want to do it?
Yep. Okay. So I'm inclined to have stuff from one side, like the battery goes in.
Yep.
And then the other side is like the motor goes out.
Sounds good.
So just drag P2 somewhere like there.
Yep.
Do I line up on the holes? Doesn't really. I'll just.
It's a grid. You can line up on the grid if you want to.
And then on the other side, I want the motors coming out. Got leads for the motor, so P1 for the motors. So I just put it the other end over here. It's a bit logical. And then off the side is the switch somewhere. So P3 rev switch. I'll park it down this corner here. Right. And then this is the order. So there was a. I can either do a diode or a... Yeah, I'll do the diode, okay.
So see how you got the blue wires?
Yep.
It's called rat's nest.
Rat's nest?
Yeah.
Yeah,
It's unconnected wires.
So,
Sorry, unrouted wires.
Okay.
So see how it's overlapping?
Yeah, okay.
So P1 is the motor, isn't it?
Yeah. Well, actually, I'm thinking about this... I mean, this thing could just be this way, right? I could flip that around, can't I?
Yeah. Then you
Okay.
go to rotate left.
Oh, sorry.
Oh, it doesn't matter, rotate right or left.
Okay, here we go.
Maybe P2 needs to go down there and P3 needs to go up there since it's connecting up to that.
Okay. Oh, yes, I see. Yes, okay. That looks...
And then you need to rotate that.
Oh, yes. Okay. Oh, like that? That's okay. I could do that.
If you want to, yeah.
I'm just going to be a bit crowded. I'm just going to rotate it again.
Yeah,
It's getting a bit tight. Okay, here we go.
See how that rat's nest is going at an angle?
Yeah.
It's always good to keep that lined up.
Yeah, so it forces
So
a straight
just-
copper line.
So just a straight copper as opposed to
Yep.
going off on a weird sort of tangent. Right mouse button, click hold, and you can pull the sheet.
Okay, great. What else I got down here? I've got. Let's bring this up. Might have to rotate that one as well because that one's connected to this one. So
Yeah.
I'll just
You could probably rotate it around so it's lying flat.
Yeah. Oh right. And also, I just realised that this MOSFET is actually sitting like straight down. It's not bent over flat. You know?
Yeah, so
you could
you've actually got to leave space for the MOSFET to lie flat.
Well, that might be the space here then.
See that tab along there?
Mhm.
That is the metal part.
Well, in that case, I'll have to. If I'm going to do that, then I'll have to drag it down, and then it'll bend up against this space here, so I'll get some space.
Now, theoretically, we should actually allow enough space. I've got a little package here, which is your voltage regulator.
Yeah.
And we could probably allow 20 mils. So you need to allow 20 millimeters from
The pin.
the end of the package to this point here.
It might have to be across the whole top.
What you could just spin it around that way.
Spin it around what?
This way, so it's like
Okay.
vertically.
Yeah. Okay.
Rotate left, rotate right.
Yeah. There we go. I need to save some space here, so there's like a safe zone of 20 mil, right?
You want to try and minimise the amount of
Track length.
crossovers, but bring up the other components and see how they look. When you're designing a PCB, it's a real art form.
It's like a tangram. Well, no, it's like fitting a moving truck full of stuff.
I mean, it's funny thing engineering. You've got two sides to it. You've got the schematic side, which is a very left brain side thing to do.
Yeah, like logic.
Yeah.
Like flow of.
And then you've got the PCB design, which is the right side.
Yeah, which is like just
It's creativity.
dealing with your physical limitation issue, right?
So I push that one up. Yeah, what I tend to do is I roughly place the components where you know there's a minimum amount of crossover, and then start jiggling and lining things up.
Big fat diode here in the way though, and I got this thing here. I could squeeze this into the middle.
What do we say, 20 millimeters?
Yeah, so these are 5, 10, 15, 20 up here.
So you can rotate that diode and around that way and push it up.
Oh, what a squeeze. You're not meant to have diodes hanging over the edge of a PCB, right? It's not really good form.
No.
Now I've got this line here.
What you could do...
Hang on a second.
You could move... See how you got P1 which connects... So pick up P1 for a second and then move it down to here.
Let's crossover.
There is a crossover there, and you got to think about well, people mistakenly. What is P1? P1's the
the motor. Yes.
Okay, so you might want to chuck it back over the other side.
Yeah. Okay. Well, that's the thing, you know. If I want a piece of copper track on the other side of this board, I mean, sorry, this is logically I'm looking at the top of the board with my components, and on the other side of my copper tracks, right?
Or you can have the copper on this side
as well.
Oh yeah.
Oh yeah, I suppose you could.
There's actually no difference in pricing from JLC.
Oh, so you say two layer, you mean the copper's on both sides of the board. Well, here's the thing though, I need space for those tracks. So like this little big hole here, I can't have a track going too close to the holes.
Correct. So what you could do is shift that down, that diode down a bit.
Yep. Oh yeah, okay. It's just that bumpy.
So then you've created a wide space for you to run a track.
See how that sort of bumps from one to another? Like this line here.
It'll show the nearest.
Show the nearest one. Right. Can I make the track now?
Yeah.
All right. How do I make this track on this board? So
well,
I'm trying to
get
get
to that little PCB option up there.
So I want to get from here, and then.
Now see how it's a really tiny track. You want to make it as big as.
Because it's carrying current.
Yeah. 40 amps. You want a big, chunky wire, and because you got two layers, you run the same track on both sides.
Okay. Is there like a ampage rating for a piece of copper track?
Well, it depends on the ounce. PCBs are usually 1 ounce on a copper. You can get 2 ounce, which is twice as thick. But I'd make that track as thick as you possibly can. 5 millimeters. That's tiny.
Okay.
So change it to try 2. Yeah, look at that. 2 millimeter. Probably.
It's like an amateur in paint. Here we go.
Now, see, this is the problem.
What?
These headers are slightly too small.
They're going to touch each other.
So you probably need to, instead of having 2, you probably need 1.
A single header.
1 by 2.
Yeah, it's 1 by 1.
Yeah.
Okay.
I mean, there's 2 ways of doing it. You can keep them there, or you can edit package.
If I go back to this diagram here, where is high current flowing and where is low current flowing? You know what I mean? Like here, I know in this little area here,
essentially
and the switch.
This
switch, this part,
everything from VCC through P3, down through here is low current.
Yep, and this one here as well.
Yeah.
Right, but from here on this side of the MOSFET and this side of the MOSFET is where
the high current.
Yeah, and the motors. Okay, so we know where we need to have really thin. We can have thin copper. Yeah. Let's change our P1 to two separate headers.
Yeah. What we can do is instead of replacing it, we go to libraries. We've got header. I'll just use a 1.
Yep, and then just have a space that's
so I've got 1 there, 1 there, 1 there, 1 there.
Okay.
So delete those and join those back up.
Now it's got an old version here.
Yep.
So just refresh or something.
Import changes. There we go. Apply changes. Now you've got separate pins.
Yep.
One thing you can do is just have one at the top, one at the bottom. So you have a whole lot of separation between VCC and ground.
That's pretty good. I mean, if I was to fit that around all those copper tracks together, that's pretty good.
Now, one thing you can do, because it's a 2-layer board, what you can do is you can add a copper area. So what we're doing is we're filling in that area.
So we're telling the computer that's going to be running that. This area is by default going to have copper in it.
Yep. So so now it's filled the top layer.
Is it like a shorting issue there, like a potential?
Potentially, but so we might want to say we want 0.5 mil clearance. So that's the top layer.
So if I was to get this board, I'll be putting my components on the same side as the copper.
Yeah, or else you can say, well, let's just switch to the bottom layer.
Yeah.
So now you've got the top and the bottom layer. So that's what it looks like. That's probably a bit better. So you don't really need this anymore, you don't need that anymore, because it's all connected from the bottom layer. So what you can do is then actually delete it. So there you go. You've got your nice big ground plane on the bottom.
SD card size.
Yeah, so what you could do is you could actually probably optimize a little bit more. Like you could shift that up, you could shift that, you can shift it around if you really want to. I could just run with that. So now that we've got our basic PCB designed, in the next video we'll be taking a look at PCB optimization, some panelization techniques, and finally ordering the PCB from Easy EDA. Thanks for watching, and see you next time.